So today I'm going to be speaking with Sesh here about an engine we've built at Trifacta called Photon, and start with some of the motivation from our product, which is a data wrangling product, of why we built Photon and what we mean by the immediacy that we needed in our user experience that led us to invest the time in developing this technology. I'm going to clarify what the technical challenges were, why this is a hard thing to do, and they're pretty substantial. We'll talk about the architectural context of the product and how this fits in. This technology is part of a larger sort of vision of how to build these things. Sesh will share with you firsthand our experiences with building this stuff in JavaScript the first time around, and the pros and the cons of that experience, and why we ended up moving towards Photon. And then we'll give you an overview of the clean slate design that we did there, which will be launched this year. Okay. So background, and let's go way back to sort of the turn of the century. When we started this company, and long before we started this company actually, we were thinking about data transformation, and the interfaces that people were using in those days for data transformation looked something like this. I got this as a screen grab from the Wayback Machine. So this is an old PDF from Informatica. I took out a picture of their interface. And you can see what these interfaces look like. They're schemas and annotations on data. So if you had to transform data, you would have sort of a canvas here where you could pull up the names of tables or the names of data sources, and you could double click on them and see the schemas, the columns and types associated with those data sources. And then you could plumb them together with these sort of box and arrow programming with a canvas of operations, things like joins and filters and renames and so on. And each one of those little icons that you would drag onto the canvas, you double click on and fill in the parameters. Okay, and so these icons don't themselves necessarily know what to do. You have to kind of double click and fill in all the details, right? And so this is really a form of programming at the end of the day. It's just programming that has a bit of a user interface. Instead of typing a command and a bunch of parameters, you drag something from a canvas, you put it on the thing, you double click, and you type the parameters. But it's fundamentally programming. And so you would do this programming in this environment that's sort of at the very high level of what does my data look like in the large, and how do I plumb data flow from it? And then you'd say go. And then execution would happen in batch. And then you'd look at the output of the job, and if it wasn't right, you'd go back to this interface and change some of those parameters or rearrange the data flow. So that's kind of the user interface, the user experience at the turn of the century for data transformation. Now, around that time, I was working with a graduate student at Berkeley on how we might make this a little bit more data-driven and hands-on, more of a direct manipulation interface, kind of like spreadsheets. So he built a tool called Potter's Wheel, which he built in Java, which would take real data, not just the names of the data, but the actual data itself, and put it up in front of you. So you were looking at the values in the fields. He sampled that on the fly from a stream of data coming in off of a disk drive, if you will. And then he would show you samples as that thing was streaming in. And the transformations were done sort of menu-driven. So rather than have a canvas with icons, there were menus with commands. You'd pull down a command, you'd apply it. And the key thing was immediately that command would be run on whatever was on the screen. So whatever data in that sample was on the screen, you'd see immediately what that command did to the data. So you got this instant feedback on the commands that you chose. And all of this stuff was done with this command language that was kind of formal and nice. So it was a domain-specific language built into the tool. So that was a tool called Potter's Wheel, which we presented on September the 12th, 2001. I remember it very well. Some 10 years later, this project kind of sat on the shelf for a while. I reunited, so to speak, not with the people, but with the ideas, with a new cast of characters. So Jeff Hare, who's a user experience expert and was a professor at Stanford, and his student Sean Candell, who we ended up co-advising, to build what was called Data Wrangler. So Sean built Data Wrangler. It was something like Potter's Wheel in that it had direct manipulation with real data. On the one hand, it was a little less ambitious because it just worked on browser-sized data sets. Okay, so all the data you can paste into your browser window with the command V. Okay, but it added some significant intelligence a decade later to the experience. So this was a user experience where the user didn't do all the work of specifying transformations. Algorithms in the background, machine learning algorithms, would help suggest those transformations. And you'll see what I mean very explicitly in a minute when I run a demo. But we call this predictive transformation, where the user basically highlights features of the data. They point at things in the grid that they think are interesting, and then they get suggestions for transformations, and they can choose from those suggestions. So they get multiple choices of what they might want to do to their data next. And they get immediate feedback on all of those choices. So as you hover over these different suggestions, you get a different preview of what the output would look like. Okay? So it's a much more sort of assisted experience where algorithms were helping you, but it preserved that immediacy that had been part of the Potter's Wheel idea and that direct manipulation, hands-on view of the data at all times. And you can see in both of these cases a very different and more immersive experience than what we had with those boxes and arrows on a grid where you had no idea what the data actually looked like. You only knew the names of the columns and the data types. All right? So Trifacta is, was born of Potter's Wheel and Wrangler. It was grown from these research roots. It's obviously got many, many more features. It's had years of engineering time put into it, whereas the previous things were graduate student prototypes. So it has deeper and broader predictive transformation. It's able to deal with massive data sets by leveraging things like Hadoop and Spark. But we use a sample-to-scale scheme, which I'll describe later, with what we call intelligent execution to make sure that both you have an immersive and immediate experience in the UI, and we can choose the right backend to execute on at scale. And then it has quite a bit richer interactive visual profiling, which neither Wrangler nor Potter's Wheel had. OK. So I want to make sure to emphasize in this demo the immediacy that we get from the user interface. So I'm going to do a very short Trifacta demo, mostly to motivate what the performance challenges are that we were trying to solve. They all come from that user experience. That's what's driving this whole business that I'm going to talk about today. So I need to give you a flavor of that experience. So what we're going to do is we're going to look at a little bit of Twitter feed data. So this is a JSON file. It doesn't show up. It didn't show up. Oh, I'm going to need to do this like this. This is a JSON file of Twitter data. So this is what Twitter feeds look like when you get them through the API. We've unnested at one level. So each column here is a key in that Twitter JSON file. And you can see they're nested. So for example, dates, the created at date has a date and a time. And we can interact with this little histogram, and predictive interaction suggests that maybe by interacting with that histogram, what I was asking for was to unnest that data. And we see a preview here of what would happen if we unnested it, including the data types of the columns we would get if we unnested it, and a distribution of the values in those columns. So immediate context as to what would happen, what would the data look like if we added this step to our script. And so let's do that. And now we have, this is a little hand-eye coordination game. Now we have the data unnested, we can drop the original column. And I'm going to go through this very quickly to give you a sense of the user experience. It's really the motivation for doing this. Similarly, we can actually look at the individual tweets, and we can highlight, say, an so a username, okay? And we'll get a raft of suggestions from Trifacta as to what we might want to do based on the fact that we seem to have highlighted a username. One suggestion is to extract those usernames into a separate column. We see a preview here. And since that's the first recommendation, we see a preview in the grid. A second suggestion is to count up how many ats there are in each tweet, to count that pattern. That's actually what I'd like to do here. So I'll take that suggestion. And when I click on it, I get the full preview up here. But note that I got a mini preview down here as well. And I'll add that to my script. So now I've got for every tweet, how many people did that tweet shout out to? Okay? We could do a similar thing, for example, to pull out hashtags. All right? So we can highlight an example of a hashtag and get some suggestions for what to do. We might extract them. We might want to replace the hashtag with something else. I'm going to look over through all of these suggestion cards at the bottom, each of which you'll see has a preview, until I find one I like. And this is the one I want. Extract a list of all the hashtags per tweet. OK, so now I'm getting out all the hashtags in every tweet pulled into a separate column. Add that to my script. OK, let's move over to the right a little bit. And there's a field here, which is a more deeply nested JSON field, which has a whole bunch of keys for a user. And rather than sort of try to highlight them here, let's just open up an individual user as an example. I want to get the screen name out from these things for everybody. So I'll highlight screen name. And it'll get the idea that I'm interested in screen names nested here and suggest that I unnest the screen names, which looks pretty good. So that's that suggestion. I like it. I'll take it. All right. And maybe there's some other things I want to pull out of here as well, but I think we're getting the idea. Let me give you one more example of, well, let's pull one more thing out. Let's get a quantitative variable like friend count for that user. Okay, this is all comes typically from a Twitter feed. So we can unnest the friend count. That's another first suggestion. So that's good. OK. Finally, let's take the screen name column and let's try to group by per user. Let's see. So Actually, I'm not going to go through this just right now, but you get the flavor of this user interface. Every time you touch something, a whole bunch of things happen in the user experience. You get lots of suggestions, you get lots of context, you get lots of visibility into what could be and what would be if you chose to do it. All right? So let me switch back to the slides. That wasn't intended to really be an exhaustive demo, just a flavor of the user experience. But let's reflect on what we just did. What was the point of having all this immediate feedback, really? I mean, why not just go back to the world of that canvas and the icons? Well, at least 3 sort of high-level user experience goals. One is to understand what's possible. So in the Potter's Wheel tool with its drop-down menus, or in that canvas that we saw in Informatica, the way you know what's possible is you read a list of commands. Right? But that's not really very satisfying. When we saw all those suggestion cards at the bottom of the screen, it was very clear what was possible with this data because the user interface actually executed all those possibilities for us and showed us previews of their outputs. Right? So that immediacy was actually even one step ahead of us of kind of playing the chess game of what would be the next move that you might want to make and showing you what would happen if you took that move. Right, so that helps a user very much go from having to think like a programmer to more thinking like a data analyst. They look at the data and say, I want it to look like that. Right, so that's very important. It helps understand what's possible. It helps the user confirm intent as well. When we were in that Informatica thing, you didn't know if your steps were right or wrong until you hit run on the whole pipeline. Right? So it's very hard to know if what you said is what you meant and if the system understood you. Here, confirmation of intent is very direct. Every time you touch the screen, you get previews. You get a sense of the system's doing what you want it to be doing. And then finally, assessing progress. Am I making progress as I go through my transformations? Is this all making sense? And you get that feeling very directly by seeing step by step how the transformations you're building fit together and make your data more what you want. Okay, so these are some of the user experience desires that we want to get out of immediacy in our user interface. Now, user studies over many years have studied what people perceive as being immediate. And one of the nice things about studying humans is they don't scale with Moore's law, right? Humans are pretty similar from decade to decade. They don't speed up much. So the human understanding of what is going on in front of them has been fairly constant in user studies over decades. And what these studies have shown is that people perceive instantaneous interfaces as interfaces that respond in roughly 1/10 of a second. Right? And these are order of magnitude sort of numbers. When you talk to people about whether they get distracted or whether they stay in the flow of their thought process, that flow is sort of, if you can get feedback on the order of a second, they don't get distracted, they stay in their flow. And if you get beyond 10 seconds, you lose their attention entirely. Right? They're often doing something else. Right? And then that last bar may be the one bar that's changed over the last few years. I would guess that that bar since the 90s has moved to the left because of the many distractions we have in our lives. But the first 2 bars are pretty good. And when we talk about immediacy in the context of data transformation, which is a very focused task, mind you, we want to be somewhere between that buttery, instantaneous feel of everything just is smooth and that 1-second flow. That's a good zone. We don't want to be getting towards 5 to 10 seconds. That's where we're going to start losing people. Okay, but we do, because this is a concentrated technical task, we do have the latitude to be in the kind of 1 second to 2 second range. So that's the performance regime we want to be in. Now, you might ask, in this user experience we looked at, and this is why I wanted to show you the demo, was to be able to really walk through this. What would happen if we took away the immediacy of the interface? Okay? Well, we wouldn't be able to get our suggestion previews, right? The big preview of the first suggestion, but also those little mini previews of the cards that helped us choose which card was the one for me. So those go away if we don't have immediacy. Or what else goes away? Well, these profiles at the tops of the columns that tell us what's the distribution of our data in those columns, those are computed on the fly based on real data. And as you transform the data, new ones are computed instantaneously. You saw when I unnested the dates and times, we suddenly had distribution of time, which we hadn't had before. So these are happening immediately as you interact, and those would go away if we didn't have immediacy as well. What else? These data quality bars, which we didn't really work with much, but at the top of each column there are these data quality bars coloring whether the data is good or what percentage of it is good. That would go away instantaneously if we didn't have immediacy. And in fact, the summary statistics of the data also are being computed on the fly because, of course, as we transform the data, we get different numbers of values. We sometimes can even get different numbers of rows if you unnest things. All those summaries are done dynamically, and those would go away too if we didn't have an immediate execution. All right? So finally, and almost most importantly, the actual data, right? We've been showing data to you, and that data changes as we transform things. So it's computed on the fly. If we don't have an engine that's immediate to show you that data, we have roughly nothing left in the user interface. We have the schema, and we have the transformation script that we're building up on the right, which is roughly what we had in Informatica, right? Except that they had a picture for the schema, for the transformations on the right. But we're back to programming. So without that immediate feedback, we're back in a world of programming, which really requires a more technical user, and is even for a technical user a much less satisfying, much more 20th century experience. So I hope I convinced you that this idea that you want to get feedback and you want to get it within a second is critical to a 21st century user interface. I hope you understand why that's so important to us and why we invested in building a new engine for this. Oh, you do get a go button. That's good. So you get some interaction. Sometimes people call that interactive query. You specify your query, you work on it really hard, and you press go, and then you get an answer. Some people call that interactive. That's why we use the word immediacy. We need it to be richer and faster than just the go button responds without me having to go for coffee. Okay, so I want to draw that distinction of immediacy. Okay, is this hard? You bet your buttons it's hard. Okay, so let me tell you why it's hard. And this is also why this is a bit different from building a query engine, all right, which is something I've been involved in many times during my career. First of all, there's this performance regime. Second of all, we have to deal with scale, because we're going to go to Hadoop-sized data sets. And third of all, we have to deal with the dirty details of dirty data. So let me carry you through this stuff. As I said, this user flow, we've got like a 1 second, maybe 2 second window, okay, to get this stuff done. All right, so that's the performance thing. We need our users to stay in the flow. It's an iterative process doing data transformation. Very hard to write the whole script and get it right the first time. You really want to be building it as you go. So we need to keep the users in the flow with that 1 second order of feedback. Scale, so lots of people at Strata will be talking about scaling up, right? That's a typical theme here. So what's different for us? Well, here, we're scaling the unknown. A lot of times when you're transforming data, you've never seen it before. Maybe no one's ever seen it before in the context of a data lake. And so you're trying to scale up, but you don't have the luxury of information about the data that's been pre-computed. This data is never seen before. That means you may not know what the schema is. It's not been indexed yet, because you haven't even pulled the structure out that you could index. There's no summaries of this data, right? There's nothing to help this go fast. You're going to have to scan all the data to do anything. Right? Many times if somebody shows you a petabyte of data and then shows you interaction, and it's real instantaneous, it's because they pre-computed everything they need to do the interaction. That's what makes it fast. I can tell you for sure that just reading from flash drives, from RAM, just reading terabytes of data through processors takes a very long time. All right? But that's the regime we're in. We're trying to scale the unknown. We don't have the luxury of pre-computation. So set that aside from your thought process here. That's one of the things that makes data transformation harder than, say, business intelligence cubing, right, where you pre-build all the structures. All right, and then let's talk a fair bit about the dirty details of dirty data. When you unbox a new data set, you don't know what's in there. The one thing you know is you should expect the unexpected. All right, this is data that's going to be dirty. It's going to have exceptions, and this raises a whole bunch of issues. 6, in fact, that I wanted to talk about. The first being ambiguous schemas, heavy string processing, ambiguous types, noise and exceptions, limited filtering, and rich transformations. So let me start with ambiguous schemas. This is a typical file. This is a call detail record file that you might want to find in a data lake and transform. All right? A little hard to pick apart what's going on in here, and it might be in the eye of the beholder what this data is, in the sense that you may transform it differently to do your task than another analyst would to do their task, so that it's not clear that there's a single way to interpret this data, in fact. It's ambiguous in a very real sense. We do a lot of string processing in data transformation. Okay, so for example, when we split up that file into columns, we might highlight a tab character, and then we'll get suggestions down at the bottom for how to split things up. Note the text of those suggestions. It's like regular expressions, if you're a technical person, is what's going on there, but it's string patterns, all right? And I can tell you, and if you don't know this, one of the most expensive things you can do with a modern processor is string processing. Right? If you can encode everything as integers, modern processors go super fast. If you're working with strings, things will be significantly slower. We are working with strings, okay? And that means you have to pay attention to how you're going to bring those strings into memory and manage them. You have to be very careful about this stuff and do it well. And languages like Java, for example, don't do efficient jobs with this kind of stuff. You have to really think at a low level about how to deal with string processing. Types in these things are often ambiguous. So for example, this first column, I happen to know this is the International Mobile Subscriber ID. okay? Because I've seen telco data before. So is it a string or is it an integer? Well, that might depend on what you're trying to do with it. But you'll notice that in this file, sometimes it has dashes separating components of the integer, and sometimes it doesn't. You get to choose whether you want to treat this as a column full of text, which, by the way, will be a little bit slower, or a column full of integers, which can be encoded more quickly and pushed through the processor faster. But that might depend on your application, and the system can't decide for you. You're going to have to work with the system. And suppose you say it is integers. Well, now you've got exceptions, because you've got a column that's supposed to be integers, and you'd like to encode it to be integers. But a lot of the data isn't integers yet, right? And you might have to say how to turn it into integers. So now we've got an encoding problem under the covers of something we want to be fast, but we have to deal with exceptions all over the place. Traditional tools like the pig language, for example, if you give it bad data, it barfs. It just crashes, right? In a relational database, they wouldn't let you insert this. They don't handle this case, right? So the engine you build is different. Another thing that query engines that I've built in the past benefit from, and we often don't, is the idea that you filter data as you're processing it. Your typical SQL query optimizer, its reason for existing is to throw away data early in processing so that downstream processing goes faster. And when you type an SQL query, the optimizer is trying to figure out what to do first that'll throw away as much data as possible, right? It's like looking at your where clause and filtering out tuples. In data transformation, for example, if you're splitting these rows by the tab character, you're not throwing anything away. Right? We're going to go through every row and generate a new version of it. And this happens all the time in data transformation. We get a lot less benefit from throwing away data than you'd get in a traditional query plan. And so we really have to be fast, because we're not going to get a query optimizer to pick a trick that's going to throw away a lot of the data. All right. And then one of the other things we do is fairly rich transformations. You saw how I unnested JSON, right? That's a thing where we're turning data into schemas. So we're turning fields in that column 1 into column names in the subsequent columns. These are transformations you actually can't say in a language like SQL. These are second-order logic transformations. So we don't have such transforms in traditional query engines. All right, so to summarize, on the performance front, we have to keep our users in the flow. We have to deal with scale in the sense of scaling the unknown. So the solution to scaling is not pre-computation. And then we have to expect the unexpected without that slowing us down. So with that as background, I'm going to hand off to Sesh, who's been one of the engineers that's been building this stuff to try to deal with these challenges.
Thanks, Joe. So we kind of picked up where Joe, Jeff, and Sean left off with the Stanford Wrangler architecture. You've kind of seen the Stanford Wrangler before. Let's break down how kind of it was put together. You had the visualizations there. You've got histograms. You have quality bars. We use a JavaScript library called D3 that one of our co-founders, Jeff Hare, invented with one of his students at the time. And this is possibly the most popular library for building data visualizations in the browser. We start off with that. And you can do interactions with the visualizations or things that you see on the screen. Maybe you select some text. This generates statements in a DSL, domain-specific language that we call Wrangle. And that goes through our DSL compiler and gets compiled into JavaScript code. And the JavaScript code executes in the browser. So fairly simple. In the browser, we go back and forth between execution to the visualization, and it's all good. What if we want to handle data that doesn't fit in the browser? Well, this is where around 2012, we kind of enter Hadoop. We want to take some data from Hadoop and do something with it. Well, the way we do that is we take our same Wrangle statements, we take our DSL, and with our DSL compiler, add another execution target. Compile down to Hadoop, execute at scale, and that solves that. The problem is, when you execute on Hadoop, Hadoop is just not interactive for any scale of data. How do we kind of bridge the immediacy with the scale gap? The answer is basically we do what any savvy data scientist would do. Just take a sample of it. So take a sample of a nice meaty sample of data from Hadoop. Wrangle that in browser to your heart's content. Do interactions, select some text, do some unnesting. Trifacta is translating everything into its domain-specific language at this point. And once we're done with all of our wrangling, we execute the final wrangling at scale and across the full data set. Now, our job on Hadoop is configured not just to return the results, but also profiles of columns and some interesting rows as well, so you get a better view of your sample. And this process we call our sample-to-scale methodology. And so this worked fine for a while, but we realized that there's a certain scale of data sets where Hadoop is, all the machinery of Hadoop is just not necessary, but the data doesn't quite fit in the browser. And so for that, we took our JavaScript engine and said, well, we can run that on the server too. And so now you have a little more of a responsive experience when you hit the Go button as well. And over time, as customers started asking for Spark, we added, we have that engine too in this kind of spectrum of responsiveness to scale. So we kind of have, we want to make sure that we use the right engine for the right job. So we have this intelligent execution layer that will automatically pick which engine you would prefer to use for a given job. And we'll do this on the fly. And this architecture we could then take and deploy in a number of different scenarios. Your typical enterprise does this on-prem style deployment, but we had customers who wanted to run us on AWS as well. So we run the Trifacta server in the cloud, and we have our browser front-end application. But the important thing here is the cloud is not on the immediacy path. All of your immediate wrangling happens in browser. We took this architecture and stuffed it into the Trifacta Wrangler app and shipped that to a bunch of people, and that's a free download on our website. And again, the immediacy path is local. Data and computation stay on your computer. So we were kind of happy with this for a while, but over time we started seeing that our JavaScript engine wasn't really performing as well as we wanted it to. Let's dive into why. So why build the engine in JavaScript in the first place? Well, we had a lot of JavaScript expertise within the company. We had our co-founder, Jeff Hare, who, and a bunch of people who were pretty deep in JavaScript at the time, and that's, it basically calls back to our roots of coming from this open source Stanford Wrangler project. JavaScript does run in the browser, and that makes it a very easy distribution vehicle, and it also runs on the desktop too, or on a single node server. JavaScript's also dynamically typed, and so that seems like it's a fairly good property for an engine that has to deal with such different varieties of data. And it's kind of where all the energy is today when people are building data-centric apps. So the question that we were asking ourselves back in around 2012 was, will JavaScript perform and will it scale? Initially, we thought the answer to this would be yes. We looked at a prototype written by our co-founder, Jeff Hare. He built this engine called Datavore. And what it was an in-memory column database. And it had some pretty good performance being written in JavaScript. But over time, we found that it was fairly hard to extend this engine performantly, since making changes to this would require modifying the guts of the engine. To make JavaScript fast, you basically have to remove function calls inside loops. And so there's this kind of impedance mismatch between what it takes to make JavaScript fast for data processing and what it takes to build software fast. And that doesn't quite fly at an agile startup like ours. We also ran into some other issues. That type ambiguity that we used to like so much, well, that started causing inconsistencies with more strongly typed engines. And when you feed something in the JVM, something that is supposed to be of another type, it is not happy. I can tell you that. It also slows down your core engine because every time you switch on type, well, that's some additional instructions that your system has to do. And that just won't fly. We even tried code generation in JavaScript. And code generation is quite interesting. You can get the body of a function in JavaScript, and you can then create new functions as well. So we tried doing some analysis. We tried swapping out attribute getters and making those direct accesses to arrays. But inlining those calls just proved to be not worth it. It was A, difficult to debug and maintain, and B, it just did not give us the order of magnitude performance gain that we were looking for. Also with our JavaScript runtime, it's fairly difficult to get true multi-core parallelism in JavaScript. You can do certain tricks. You can play certain tricks in the browser with web workers and what have you, but it just doesn't work beyond a certain point. It doesn't provide that functionality natively. We also saw some pretty weird behavior with memory usage in JavaScript. We were seeing some fairly small data sets blow up in memory usage because of the nature of JavaScript being a garbage collected language. And that's one thing that I'd like to call out and say that's not just a JavaScript problem, as we'll see later on. So it's pretty clear by this point that we had to ditch JavaScript. Well, what were our alternatives? We're kind of already compiling our Wrangle DSL to something like Spark. So, well, why not run Spark and just use that as our interactive or immediate engine? To do that, we wouldn't be able to run the JVM in the browser, so we had to put that server side and then incur cloud latencies, which is something that we didn't want to do. It just didn't work for the immediacy that we needed. It limited our deployment options, and we also wouldn't solve the problem of not being in a garbage collected language anymore. So, thinking about this with a clean slate approach, we want to keep our portability. We want to keep our in-browser solution and our single node server solution. We want to, well, maybe use something that exists, but Java's just not viable in the browser. If we really wanted to go for performance, we want to manage our own memory. We want maybe a C++ or LLVM-based engine. And if you haven't heard of LLVM, this is a new compiler infrastructure out of the University of Illinois. It's been adopted by a lot of large companies and pushed by Apple and Google. And it's great for high-performance compiler work. We would ideally use something like that for building our own engine, but how do we get the portability that we wanted? And this is where we had an interesting surprise meet us. There are a lot of native code frameworks out there. For example, Google Chrome's Portable Native Client, or Pinnacle, ASM.js, and the upcoming WebAssembly. And what these things do is basically let you compile C or C++ code, ship it to the browser, and run it there. So you get rid of the JIT overhead. You can have all the dense data representations you want. You can choose how to lay out your memory. And you have no unpredictable garbage collection because you're dealing with the memory yourself. So we went with Chrome's Portable Native Client solution here because it's a fairly mature platform. It gives you an LLVM-based Clang style, cross-compilation style toolchain. And this is something that's fairly familiar if you're working with C++ code. It also has plenty of ports for some popular vendor libraries. For example, RapidJSON is a fairly popular JSON parsing library that's easy to build with this framework. And there's a website if you want to check it out. We also had some pretty good experiences with threading in here, which got us a lot of our parallelism. And we did some prototypes early on of what it would take to wrangle data using something like this in browser. And we were quite pleased with the results when we prototyped it. So moving into how we actually implemented our engine. We started off with some requirements. For the immediate feedback, we needed a less than 1 second response time for the interactions that we did. And this is something that comes out of the user flow stuff that Joe was talking about earlier. We also wanted a low memory footprint for our engine. We wanted to make sure that we were using some fixed percentage of the dataset size. So our engineering process for this was, I think, fairly interesting. We started by establishing a speed of light. And what we mean by this is the absolute best performance for doing any particular thing. So this is something that you can get by micro-benchmarking, for example. We then add features and functionality to extend it and provide the enterprises with the enterprise features that they want. And then judiciously compare what we're doing with the speed of light and make compromises if we need to ship by a certain date. If we are, however, meeting our speed of light, well, this is an iterative process. The speed of light changes with the medium that it's in. So if you're meeting your speed of light, hey, maybe you're in a different medium and you've got to reevaluate your speed of light. So we took a lot of inspiration from the community. There's a bunch of good engines out there that we learned from. And we started off by just taking our serializable and human-readable data flow description. We then sharded this data flow, mainly for multi-threading. We borrowed some strategies for complex transformations from some of these projects, like Hyper and Tupelware, and we made sure to improve our data locality and made sure that when we were allocating chunks, we did that contiguously. Let's talk about the architecture of Photon itself. So here's our familiar browser. We've got our visualizations, our front end written with D3 and other fun tools. We have the DSL compiler. And the DSL compiler then compiles down to a specification that Photon can understand. And so Photon in the browser has a little request router. Have I computed this table before? All right, return stuff from the cache. Otherwise, go down to the engine and combine the execution nodes, the core execution nodes, with some of the extensible functions and aggregates in there. Our in-memory data layout was fairly important for getting the performance that we wanted. We start off with some table metadata and some row metadata to indicate whether a particular row is valid or not. We decided to build a columnar engine where we have data stored in a columnar format. Each column has a certain amount of metadata associated with it, and we have the data itself in columnar chunks. And so each chunk over here, the green boxes that you see, are contiguous slabs of memory. And this proved to be important for a lot of the memory allocations that we want to do and for continuous scans of that data. When dealing with this data in some operator, we can't deal with the entire table at a time. So our parallelism is derived from splitting this into horizontal slices that we call row batches. Each of these row batches contains some number of chunks, one for each column of the table, and represents some slice, a tablet, if you will. A lot of these concepts we found were not just unique to our own domain, even though some of the problems that we were solving were fairly different. The Apache Arrow project has recently proposed a bunch of in-memory data structures that resemble this very closely, and that's no accident. We've been chatting with some of our friends at Cloudera and at Dremio and other places, and we've been collaborating with the Apache Arrow guys and getting this specification out. So we're excited about where this effort in the community is going, and we'd like to see what happens to it. We're tracking it closely. So let's talk about an actual data flow itself. We have something like some source operator. We have maybe a filter, a map after that, some aggregating operator, which you'll note is a barrier. It needs to receive all of the tuples before it can do anything else. We have a map after that, and then we're storing some stuff in a sink. So let's say we have some input row batches on the left. We take our threads down here. These are our execution threads from thread pool, and attach them to our row batches and can push them through as far as they can go. When they reach the aggregate node, they collapse down into a single row batch, the aggregated result. And we can keep going with the rest of the row batches. We can collapse this down too, and push that through until the sync node at the very end. And that's basically our data flow. One nice thing about this kind of a data flow where we're push-based is we get this, we get the parallelism for free almost, just by scaling the number of threads that we have. I want to talk really briefly about our development toolchain. C++ development has changed quite significantly from a decade ago. Modern C++ makes it much, much easier to manage your memory, and you have things like new container classes, you have a threading library. There's also tools that Google has put out, namely Google Test, Google Mock, and Google Benchmark. Very useful for unit testing and mocking and running micro benchmarks of certain things for making sure you're hitting the performance you want. We use CMake and to handle the cross-compilation changes we needed for our Pinnacle toolchain. And there are a number of utilities that help us catch bugs that are otherwise very difficult to catch, like are you leaking memory somewhere? Or do you have a thread race condition? Address sanitizer and thread sanitizer were useful for this. So the question we have to ask ourselves is, was all of this worth it? Was it worth implementing this entire engine to meet our use case? And the way we ascertain that is via our experiment. So on the mid-2014 Mac Pro, that one actually, we ran with an 86 megabyte data set, which had about 250,000 rows. We looked at a couple of use cases that were pretty common for us. And you'll recognize these from earlier. We've got the column profiles up there, and we've got the suggestion previews. So let's take a look at what it would take to evaluate suggestion previews in some comparable engine, like Spark, for example. We need to populate the grid with all of the contents of the computation. So looking at this graph, what we have here is on the x-axis, we have the number of columns. What we're doing is we're modeling the initial split of a data set where we're creating all of our string columns out of the initial file that comes in. And on the y-axis, you have the average time in seconds. And what you see here is, there's a little annotation down there for the user flow goal that we can set ourselves. Earlier, when Joe was talking about the limits of user focus, 1 second was the goal that we set ourselves for an immediate response time. So we're seeing that Spark's not doing too well here, and we can kind of dig into why. Here's a graph of our memory usage over time versus Spark's memory usage. And the line that you see down there is the size of the data set. While we're staying within a certain multiple of that data set size, Spark is using a large amount of data over that.
That's 2.5 gigabytes of data, right, for an 86 megabyte file, just to be real clear.
I mean, at best, it's using 1 gigabyte down at the bottom, which clearly doesn't work for our use case. Looking at the other use case of aggregating data down to get profiles, we see that we are within 1 second most of the time for both engines. This is time taken versus number of columns generated. But we still have the same memory pressure issues that we see. Now, what we found after doing some experimenting with Spark was that a lot of time was being spent in its collect function in trying to bring all the data back together into something in memory on a single node. All these things were done on a single node, but that additional work, there's definitely optimizations that could have been done to make it better, but it clearly wasn't optimized for our particular use case. And so going back to our requirements, we see that Photon has indeed met these requirements that we needed. And so some of the lessons we learned from Photon, it's fairly important to pick the right engine for the right job. We love Spark for all of our at-scale processing, and Hadoop has been widely proven to work on the largest data sets that we know of. But for the user experience, we really need that immediacy, and that's why we had to build the Photon engine. And for designing for that immediacy, that's not something that you get for free. You have to start out with that as a criteria. We found that starting by establishing our speed of light and then ensuring that we can keep achieving that speed of light as we continue building was very important. We also found that memory management and portability are not mutually exclusive anymore. There are a number of frameworks that make it easier to work with this today. And so kind of summing up our talk, we really needed the immediate data wrangling. We think this gives the user a huge value when using our product. The Photon engine gives us this user flow, it gives us lean memory usage, and it gives us the portability that we wanted. And it also complements our intelligent execution layer, like adding to Spark and Hadoop for the processing that we need. And with that, I'm not sure if we have any time for questions.